Okay. Let me actually start at the beginning, because I want to start to go over new material on matrices. And I'll start at the beginning of chapter 2. And just review matrices from the very beginning. So section 2.1 is on the vector space of matrices. So an M by N matrix is just a rectangular array of numbers, M rows and N columns, and the first row is written A11 up to A1N, and so forth. The ith row is AI1 up to AIN, down to the last row, the mth row, AM1, AMJ, AMN. And the standard notation is that AIJ is the coordinate of the matrix, the scalar, in row I and column J. And you can add and subtract matrices, and then we usually just write this as AIJ in parentheses, without writing this whole thing out. So if you have two matrices, A plus B, and they have to have the same dimensions, they must both be M by N matrices. You cannot add matrices that have different rectangular shapes. They have to have the same number of rows and columns, and you just add coordinate-wise, just the way you do with vectors. You add vectors by adding coordinates. You add matrices by adding coordinates. If you take a matrix A and you want to multiply it by a scalar C, you multiply every coordinate by the scalar C. And that's addition and scalar multiplication of matrices. If you have a matrix A, the jth column of A, you just look at the entries in the jth column, and you pull that out and write that as a column vector. So in the jth column, it's A1J, A2J down to AMJ. And they're N columns, so J goes from 1 to N. And you also have the rows of the columns, which are the row vectors. The ith row of A is the row vector you get by just taking the ith row of A. So this is AI1, AI2 up to AIN. This is the ith row. And the number of rows is M, so I goes from 1 up to M. Right. And that's all there is to addition and scalar multiplication of matrices. You can add matrices if and only if they have the same shapes. Now, you can multiply matrices, but the story of matrix multiplication is different and a little bit more complicated. So this is section 2.1, matrix multiplication. And the idea is based on the fact that if you had a row vector, say A1 up to AN, and a column vector B1 to BN, we'd multiply the row into the column. And again, there are the same number of coordinates horizontally on the left as there are vertically on the right. You take the product of the first coordinates, the products of the second coordinates, and so forth. All of the pairwise coordinates and you add them up. And that's how you multiply a row times a column. So if you had 3, 6 minus 2 and 8, 1, 5, this is 3 times 8 plus 6 times 1 plus minus 2 times 5. That's 24 plus 6 minus 10 is 20. So this times this is this number 20. A row times a column gives you a scalar. Now, if you're going to multiply matrices, if you have a matrix A, which has m rows and n columns, and a matrix B, which has n rows and p columns, the important thing is that the number of columns in A equals the number of rows in B. The m and the p can be completely different. And this product is going to be a matrix, I'll call it C, which is an m by p matrix. It's almost like the m and n's cancel out. And the rule for matrix multiplication is the following. If you have A11 up to A1n, AM1 up to AMN, and B, which is B11 up to B1P, down to this nth row, Bn1 up to Bnp. In the matrix A, you have the ith column. So you have the ith row, AI1 up to AIN. And in the matrix B, you have the jth column, B1J down to BNJ. And you have n scalars in the nth row of A. You have n scalars in the so you have n scalars in every row I of A, the ith row. You have n scalars in every column, the jth column, for J going from 1 up to P. And you can multiply this row into this column, and you get this matrix. See, I goes from 1 up to M. Here, J, the columns, go from 1 up to P. And you take the ith row times the jth column, and that's going to be, so in this matrix, C11, this will be C11 up to C1M, CP1, C11 up to C1P. This matrix is going to have M rows and P columns. And in the ith row, jth column, Aij, that number is what you get by multiplying this row into this column. So Cij is the sum of Aik, Bkj, k goes from 1 up to n. So this is the rule for matrix multiplication. And you need to, basically, you need to know it. That's what it is. It's a rule. And so if you memorize the formula in the beginning, and after a while, you've done so many matrix multiplications, there's nothing to memorize. You know it. And matrix multiplication satisfies all the nice properties of a multiplication that you would want. So if A is an M by N matrix, and B is an N by P matrix, and C is a P by Q matrix, then if you multiply AB, this is an M by P matrix. And if you multiply that by C, which is PQ, you will get some matrix D, which is M by Q. On the other hand, if you multiply B and C, this is B is N by P. Right. So B and C will be N by Q. And if you multiply it by A, which is M by N, you will get a matrix D prime, which is M by Q also. And these are always equal. That is, you have associativity of matrix multiplication. So long as the dimensions match and you can do all the matrix multiplications, AB times C is the same as AB times C. What you do not have is commutativity. So for example, if I let A be the matrix, I don't know, 2, 1, minus 3, 0, and B be the matrix 5, minus 2, minus 1, 3, just random matrices. What is A times B? 2, 1, minus 3, 0, 5, minus 2, minus 1, 3. When I multiply them, I get 10 minus 1, minus 4 plus 3, minus 15, 6. When I multiply them in the opposite order, B times A, 5 minus 2 minus 1, 3, times 2, 1 minus 3, 0, I get 10 plus 6, 6, minus 2 minus 9, minus 1. Compare them. They have nothing in common. AB is different from BA. I mean, it might happen in some particular case. You have two matrices AB where A times B is B times A, but in general, they're not going to be equal. You can never assume matrix multiplication is commutative. A basic matrix, which one deals with all the time, is the identity matrix, the N by N identity matrix, which is written I or sometimes IN if you want to emphasize the size. It's an N by N matrix. N by N is a square, right? Since the height and the width are the same. Ones down the diagonals and zeros everywhere else. So the matrix with ones down the diagonals and all zeros elsewhere is called the identity, and it has the property that I times A is equal to A if this multiplication is defined, and A times I is equal to A. So multiplying by the identity for matrices is the same thing as multiplying by 1 for numbers. So a square matrix is an N by N matrix. That means the number of rows equals the number of columns. So, and we say that a square matrix, an N by N matrix, A is invertible if there exists an N by N matrix B such that A times B equals B times A equals the identity. And we write, well, right, if also another matrix C has this property, AC equals C times A, then I can say that B is B times the identity. That's B times, but the identity is AC, which by distributivity is BA times C, but BA is the identity times C is C. So B equals C. So if an inverse exists, it's unique. And we write, so denote by A to the power minus 1, the inverse of the matrix A. So one of the basic facts about 2 by 2 matrices is A equals A, B, C, D is invertible if and only if the determinant of A, AD minus BC, is different from 0. And in that case, A inverse is the following. Suppose I let delta be this non-zero determinant. The inverse of A is going to be D over delta minus B over delta minus C over delta, A over delta. I claim that's the inverse of A. So that's check. A times A inverse, A, B, C, D. Of course, this is exactly the same. So I'm multiplying every coordinate here by 1 over delta. So this is 1 over delta times D minus B minus CA. So let me write this as, so this is D minus B minus CA times this 1 over delta. So what is this? If I do this matrix multiplication, this is D. A inverse, A, B, C, D, D minus B minus CA. So this is AD minus BC minus AB plus AB, CD minus CD minus BC plus AD. This is equal to 1 over delta times, this is delta, 0, 0, delta. That's scalar multiplication gives 1, 0, 0, 1, which is the identity. So this is a proof, if you like, that if the determinant is non-zero, then this is the inverse of A. We also have the usual rules of exponents for matrices. If you have A to the power K, A to the power L, that's A to the power K plus L for all integers K and L. Well, for all non-negative integers, then if A has an inverse, then for all negative integers as well. There's one other useful operation on matrices. Suppose I take a matrix 1, 2, 3, 4, 5, 6, say, call that A. The transpose of A is the matrix you get by transposing or interchanging the rows and the columns. So in A, the first row is 1, 2, 3, and the transpose, the first column is 1, 2, 3. In A, the second row is 4, 5, 6. In A transpose, the second column is 4, 5, 6. You could also do it by looking at the columns. In A, the first column is 1, 4, and the transpose, the first row is 1, 4. Second column 2, 5, second row 2, 5. Third column 3, 6, third row 3, 6. In general, you get the transpose of a matrix. So the transpose an m by n matrix A by interchanging the rows and columns. And you get the transpose A superscript T, which is going to be an n by m matrix And the ijth coordinate of the transpose, so aij transpose, is the jith coordinate of the original matrix. So, but really all you have to remember is this example. Rows change into columns, that's the transpose. That's all it is. And the transpose of an n by n matrix, if you interchange n and n, you just get n and n, is another n by n matrix, right? So you take 6, 2, 6 minus 2, 3, 11. The transpose, 6 minus 2, 3, 11, still a 2 by 2 matrix. So an n by n matrix is symmetric if it's equal to its transpose. So for example, if I take the matrix 2, 5, 5 minus 7, and I transpose it, 2, 5 is the first column, 5 minus 7 is the second column. It's the same matrix. So this is a symmetric matrix. You transpose it and it doesn't change. I take the matrix 1, 2, 3, 2, 4, let's see. This is a symmetric matrix. Because if I transpose it, 1, 2, 3, 2, 4, 5, 3, 5, 6, still looks the same. And you notice in the symmetric matrix, what's down the diagonal doesn't matter, that doesn't change. But the numbers that are symmetric with respect to the diagonal, 2 and 2 are the same, 3 and 3 are the same, 5 and 5 are the same. That's what gives this symmetry of the matrix. So in some contexts, in some applications, symmetric matrices are useful and important. Now, we had been studying linear equations, and there's a close connection between matrices and linear equations, which I will now explain. So this is section 2.4 on the augmented matrix. Suppose I take a system of m linear equations in n variables. This is the standard notation that we used. That's my system of m equations and n variables. So the matrix of coefficients of this system of equations is an m by n matrix that you get, forget the b's for the moment, you look at the coefficients of the variables. So A11, A12 up to A1n, A21, A22 up to A2n, AM1, AM2 up to AMN. So it's like you erase everything except the A's, and you have this rectangular array of numbers, of scalars. That's the matrix of coefficients of the system of equations. Now, suppose you take the n-dimensional column vector, sorry, the x1 down to xn, and the m-dimensional column vector b, which are these numbers on the right-hand side. So this, suppose I want to look at AX. So A is an m by n matrix. X is a column vector, sorry, with m rows. It's a, X is a column vector with n rows. X is n by 1. So I can multiply A times X. What I'm going to get is an m by 1 matrix, which is an m-dimensional column vector. Right? Let me do that. Let's just actually carry out this multiplication. So I have the matrix A11 up to A1n, AM1 up to AMN, and I have my column vector X1 down to XN. So when I do my and the ith row is AI1 up to AIN, and the ith element here, well, I don't need that. So when I multiply out, this is m by n, n by 1. First row into the column, first column, I get A11X1 up to A1N XN. When I do the ith row into this column, I get AI1X1 plus up to AIN XN. Down to the last row into this column, AM1X1 plus AMN XN. I get this vector. These are numbers. And my system of equations is exactly the equivalent of saying this is equal to the vector B1, B2 up to B sub m. Because to say this vector equals this vector means the coordinates are the same, which is exactly this system of equations. So you can write your system of equations in vector form by taking the coefficient matrix A times this vector X of variables equal to B. So this is the matrix form of the system of equations. Now, there's another matrix we associate with the system of equations. See, in our system of equations, we had not only the A's times the X's, but this right-hand side. So I want to take what is called the augmented matrix. So the augmented matrix is going to be an m rows, but n plus 1 columns. So you take the matrix of coefficients, A11 up to A1n, AI1 up to AIN, down to AM1 up to AMN, and I add one more column, the B's, the right-hand sides of all the equations. So here I have n columns plus one more, so I have n plus 1 columns. This is the augmented matrix of the system of equations. So for example, if you had a system x plus 2y equals 5, 3x plus 4y equals 6, the matrix of coefficients is 1, 2, 3, 4. And the augmented matrix, you take 1, 2, 3, 4, and then you add the right-hand column, 5, 6. So this is the augmented matrix for this system of equations. And this system itself is equivalent to A x equals B where this is A, X is XY, and B is 5, 6. So that's the matrix form of this system of equations. And this is the corresponding augmented matrix. Now, the augmented matrix allows us to do Gaussian elimination a little bit more efficiently than we did in the previous chapter. So let's just recall systems of equations are equivalent if they have the same solutions. And what can you do to a system of equations? How can you change it in such a way that you don't change the set of solutions? You get equivalent systems. We had 3 operations. You can interchange 2 equations. Multiply an equation by a scalar, or add a multiple of one equation to another. If you think about the augmented matrix of a system of equations, interchanging to it, so what is the equivalent for the augmented matrix? Interchanging 2 equations is the same as interchange 2 rows, because each row corresponds to an equation. You can multiply any row by a scalar. I should say always a non-zero scalar. And you can add a multiple of one row to another. In general, if you take a matrix and you perform any of these operations, these are called the elementary row operations, you get what we will call a row equivalent matrix. So 2 matrices are row equivalent if you can get from one to the other by some sequence of these elementary row operations. And the idea is to use elementary row operations to solve a system of equations efficiently. So let's take an example. Suppose we have the following system: 9x plus 11y equals -1, and 5x plus 6y equals 3. Actually, let me get a new piece of paper because this involves more writing. So here's my system of equations: 9x plus 11y equals -1, and 5x plus 6y equals 3. The augmented matrix is 9, 11, 5, 6, and then -1, 3. Now, suppose I want to solve these equations by Gaussian elimination. First thing I would do is multiply the first row by a 9th, so the coefficient of x is 1. So I get 1/9 x plus 11/9 y equals -1/9. And I don't do anything, doing things one step at a time. That's the second row. What's the corresponding elementary row operation on the matrix? Multiply the first row by a 9th. I get a 9th, 11/9 -1/9, 5, 6, 3. Oh, sorry. When I multiply by a ninth times 9 is 1. That was the whole point. This is 1. Don't know why I wrote that. 1. Then, when I have my system of equations, I'd leave my first equation alone. And I would take the second equation minus 5 times the first equation. So 5x minus 5x is 0. 9y minus 55 over 9. So 9 is the same as, 6 is the same as 54 over 9. So this is 11, this is 54 minus 55 over 9. This is minus a ninth y. And 3 minus 5 times this, that's 3 plus 5 ninths. That is 27 plus 5 over 9, 32 over 9. Okay. So when I eliminate x, I get this system of equations. What happens here, I have the first row, and then I add minus 5 times the first row to the second, or the second row minus 5 times the first. 5 minus 5 is 0. 54 minus 55 is minus 1 over 9. 27 minus 27 over 9 minus, oops, oh, 5 over 9 is 27 plus 5 is 32 over 9. So minus 5 times this row to this row gives me this matrix. And you see, at each step, the system of equations and the augmented matrices are exactly the same. Right? The last step, the next to the last step, I want to make this coefficient of y a 1. So leave the first line alone. Multiply the second equation by 9 minus 9. I get y equals minus 32. Leave the first row alone. Multiply the second equation by minus 9. I get 0, 1, minus 32. I want to eliminate the y. So y equals minus 32. I multiply the second equation by 11 over 9 and subtract it from the first. I get x, 11 over 9 minus 11 over 9, minus 1 over 9, plus 11 times 32 over 9. Which is 351 over 9, 39. And on the augmented matrix side, I have 0, 1, minus 32. I multiply the second row by 11 over 9 and subtract that from the first. I get 1, 0, 39. And again, this system of equations is exactly translated into this augmented matrix. So in both cases, I've solved my equations. This corresponds to the equations x equals 39, y equals minus 32, exactly what we had here. So, and in general, it's, especially if you're doing things by hand, it's easier to work with augmented matrices than with systems of equations. Okay. And in the notes, you will find many, many, many examples of, not many, but you'll find a number of examples solving systems of equations using the augmented matrix and elementary row operations. Now, what is the shape of the matrix we end up with when we successfully solve a system of equations by elementary row operations. It's in what is called row echelon form and the two related things, reduced row echelon form. And what we're doing when we solve a system of equations is putting a matrix into reduced row echelon form. So when is a matrix in reduced row echelon form? So suppose your matrix A11 up to A1n, AM1 down to AMN. So this matrix will be in row echelon form if it has the following properties. First, you can have a matrix where some rows are zeros. So every zero row is at the bottom. Every zero row, a zero row is a row where all the coordinates are zero, is below every non-zero row. You can always arrange that. If you have a matrix with a row that's zero and beneath it is a row that's non-zero, you just interchange them, right? Second, in each non-zero row, as you go from right to left, from left to right, the first non-zero coordinate is a 1. And in every other row, above and below that 1 is a 0. So for example, suppose your matrix looks like this.
Can you please move the paper?
Sure. So in this matrix, there's a 0 row and it's at the bottom. In every other row, the first non-zero entry is a 1. So in the first row, here's a 1. And in the column, every number above and below that is 0. In the second row, the first non-zero number is a 1. Everything above and below it is a 0. In the third row, the first non-zero number is a 1. Everything above and below it is a 0. So in every non-zero row, so the 0 rows are below the non-zero rows. Every non-zero in every row starts with a 1. As you go from left to right, the first non-zero coordinate is a 1. And in the column where that 1 occurs, everything else is 0. And there's one other property. As you go down from a non-zero row to another non-zero row, like here to here, the first non-zero, which is a 1, is to the right. By that I mean, here's a 1. In the next row, the first 1 is to the right of where the first one is. In the next row, the first 1 is to the right of the 1 in the previous rows. So if K1, K2, and so forth are the columns where the initial 1s occur, as you go from one non-zero row to the next, these numbers are increasing First column, third column, fourth column, 1 less than 3 less than 4. So actually that's reduced row echelon form. When a matrix is in this form, it is in what is called reduced row echelon form. And when you solve a system of equations by Gaussian elimination using the augmented matrix, what you are doing is by elementary row operations, putting your matrix in reduced row echelon form. So, and every matrix by elementary row operations can be put into reduced row echelon form. So here's an example. Let me start with a matrix that's in the notes. It's a 3 by 3 matrix. 3, 13, 37, 1, 4, 13, 2, 14, 14. So I want the first non-zero entry in each row to be a 1. Now I could take the first row and multiply it by a third. That would give me a 1 here, but that would give me fractions. It's perfectly okay, but I like to avoid fractions. So I'm just going to interchange the first and the second rows. 1, 4, 13, 3, 13, 37, 2, 14, 14. So I just interchange the first and the second rows. So now I have a 1 here. And I'm only allowed to use elementary row operations, interchanging rows, multiplying a row by a non-zero scalar, or adding a multiple of one row to another. I want to get rid of the 3 here. So I'm doing things one elementary row operation at a time. So I'm not changing the first row or the third row, but I take the second row minus 3 times the first. 3 minus 3 is 0. 13 minus 12 is 1. 37 minus 39 is minus 2. Okay. So now I have a 0 in this column. I want a 0 here. So I leave the first row, the second row alone, and from the third row, I subtract twice the first. 2 minus 2 is 0. 14 minus 8 is 6. 14 minus 26 is minus 12. Okay. So my first row starts with a 1, and in the first column, every other number is a 0. Then I look at the second row. I want this to be a 1. Well, I'm lucky, it already is, so I don't have to do anything to the second row. But I want to get rid of the 4 and the 6. So first I'll get rid of the 4. I'll add minus 4 times the second row to the first row, or the first row minus 4 times the second. 1 minus 0 is 1. 4 minus 4 is 0. 13 minus 4 times minus 2 is 13 plus 8 is 21. So now I have a 0 here. I want a 0 here. So I take the third row minus 6 times the second row. 0 minus 0 is 0. 6 minus 6 is 0. Minus 12 plus 12 is 0. Okay. So here is my 1, and everything above it is 0. And the 1 in the second row is to the right of the 1 in the first row. And now the third row is all zeros, and it's at the bottom, so I'm done. So this matrix is now in reduced row echelon form. Now, I could have put a matrix in reduced row echelon form in many different ways. There's nothing unique about the examples I picked. But there's a theorem, which is a very nice theorem, that says no matter how you put a matrix in reduced row echelon form, you always end up with the same matrix at the end. Let's also interpret all this in terms of equations. I started with this matrix. This matrix is the augmented matrix for a certain system of equations. 3x plus 13y equals 37, x plus 4y equals 13, 2x plus 14y equals 14. So if I started with this system of equations, this is the augmented matrix for it. And this matrix is equivalent to this matrix, which means this system of equations is equivalent to the system of equations for which this is the augmented matrix. What is the system of equations for which this is the augmented matrix? X equals 21, y equals -2. And if you check, this is the solution of these equations. In fact, it's the unique solution. Because this system of equations and this system of equations have the same solutions. So that's very nice. This is a very tight connection between matrices and systems of linear equations. And this is basically what's needed for some homework problems that you'll have. So I'm going to talk more about matrices in the next lecture. And then I'm going to talk a little bit more about determinants. Okay. That is it for today. Are there any questions? Just you, Emily. So
Okay, can we stop the recording and talk about the midterm?
hang on one second. Sure.
Thank you.